Okay, so this video will cover some basic statistical tests in R. The next video will go into ANOVA and linear regression in more detail, but for now we'll stick with the simpler tests. So as always, first I'm going to make sure I set my working directory. I'll load the readxl package to load in my .xlsx data file, res. Now because I'm going to be doing analysis by group, I'm going to use the as.factor command to make sure that res is being treated as a group. And then I could also do the same thing for gender here if I was going to use gender. Now, before we go on, I'm going to recode the group variable just to make interpretation a bit more simple. And this is not something we've covered so far. So we're going to open the dplyr package. Again, install this if you haven't done so already. And the command we're going to use is recode. So I'd like to recode group in the res data frame. So I'd like to recode, so again we specify group here, and then we say any value of 1 should now be mono, any value of 2 should be EAL. So if we run this and we open up our data frame, we'll see now instead of 1s and 2s we have the character strings EAL and mono for the group vector or column. Okay, and again, here we can do the same thing with gender using the same syntax. So before we start any statistical tests, let's just get some quick descriptive statistics again. So I'm going to load the psych package for this and describe by. So describe the whole data set by group. And I'm also going to specify mat or matrix true. So let's see what this looks like. Okay, so here we have mono and EAL interspaced like this, rather than having all mono and all EAL, and we can see them line by line. So we're going to be looking at numeric variables, so specifically time 1 rec, or time 1 receptive vocabulary, and here straight away we have the mean for the two groups, so we can see the mean for mono is 103, but the mean for EAL is 94. So we might be interested in testing whether these two are statistically significantly different from one another. Before we get to that, another thing we can do is look at counts in various categories. So we might want to know if there are more males or females in each group. Okay, so here we will need to use gender, so we'll make sure gender is also a factor, and again we can recode gender as we did with group. So the way we can test whether the distributions are different in both of the groups is to use the chi-square test. Now before we get to this we need another step, and this is to use the table command. So table just produces a table of counts for different categories. So here we're saying we like a table of gender by group. So for each level of gender, how many are there in each group? And if we just run this by itself, down in the console, we'll see a small table here. So this is what we're trying to produce. So in order to use the chi-square test command, we're going to have to save this into an object, and we'll just call it tab, call it anything you like. And then we put this object in the chi-square test command. And if we run that, control and enter, we get our test results at the bottom here. So our p-value is higher than the criterion of 0.05, suggesting that there's no statistically significant difference between the two groups in terms of their gender distribution. Okay, so the next thing we might want to do is to run a t-test. Obviously there are different versions of t-test, and as a general caveat I would say that there are lots of different ways of carrying out statistical tests in R, lots of different arguments you can use depending on your specific questions and your data profile, but these are just some kind of placeholder examples. So to do a t-test we use the t.test command, and we say we like the dependent variable time 1 rec as a function of group. Paired is false because these are independent groups, not repeated measures. And then we have this var equal command, so whether the variances in the two groups are equal or not. You can change this to f if they're not. By default, R will produce a t-test assuming that variances are not equal. So that's equivalent to saying f here. Okay, and if we run that, let's see what we get. So it comes up with Welsh two-sample t-test, and you'll notice that the degrees of freedom is not a simple integer. And this is because R is assuming that the variances between the two groups are not equal, and therefore it's not running a student t-test. One way we can check is to use the Bartlett test, and this is a function built into R. So we'll, again, same syntax as above, time1 rec as a function of group. We run that. Here our p-value is, again, not at the criterion level, so that suggests that there's no evidence to suggest different variances between the two groups. In other words, we can assume that variances are indeed equal. So if we can go back up here and change f to t and run this again, now we'll see that we've got a two-sample t-test, and our degrees of freedom is what we might expect. It's a simple integer. Note in this instance that the p-values are very similar, whether we specify var equal true or false, but this is an important feature to know about. If we're dealing with non-parametric data, we can request a Wilcox signed rank test, and that's wilcox.test, and again the same syntax as above, time1 rec as a function of group. Okay, and here we get an error message about computing exact p-values with ties, and this is something you can find out more about online, but again the p-value is very similar here. Okay, next is correlation. So we can compute a single correlation between two variables quite easily using core. So here we'll compute the correlation between time1 expressive and time1 receptive vocabulary. We'll run that, and that will give us the R down here, 0.68. If we want more information about this, we can use the core.test function. I would always recommend this above core because, as you can see, core is very sparse. So core.test, same syntax as above, and this time it will run a statistical test for us and we get a p-value. Note that we're using scientific notation here by default, and if you'd like to turn this off, we specify options, scipen, and then a sufficiently large number like 999. Okay, and if we run that again, this time we get the full figure, so we can see exactly what it is. Okay, so that's a simple correlation for one pair of variables. Note also that there are a couple of things we can specify. So if we have non-normally distributed data, we can specify Spearman, and we've got other options as well. So we can use all observations, we can use only pairwise, or pairwise complete. Okay, one thing that's very useful to do is to get a correlation matrix for a whole range of different variables. So I'm not able to do this with my data because there aren't sufficient variables there, but what we'll do is we'll look at some built-in data in R. So this is a built-in data set called state.x77, and basically we're just going to say we're going to create an object from this in our environment, and here we are, states. So we have a range of US states, and then for each one we have some indicators along the top. So what we want to do is produce a correlation matrix of all of these, and the psych package will help us here. So not only will it produce a correlation matrix, but it will also produce underneath a separate matrix of p-values for those figures. Okay, so if we run this, let's see what we get. So the first matrix up here is just the correlation matrix. We've got negative values, we've got positive values. Of course, it produces the whole thing, and you'll just have to ignore the top or the bottom triangle. Okay, and at the bottom we have probability values, so we have the p-values for all the different combinations as well. So this is something that's useful to put together. Okay, and so those are the simple statistical methods we'll talk about for now. In the next video, we'll discuss ANOVA and linear regression.